to the next talk, which is an invited talk by Kishalay Day from MIT. He's going to talk about obscure transients in the galactic plane with the Roman Space Telescope.
Okay, can you hear me?
Yes, but I don't see your slides yet.
Yes, let me try this. Is that, you see this?
It's good. Yes.
Okay,
Yes.
Perfect. All right. Okay, so starting off, so thank you to the organizers for inviting me to give this talk, and thank you to everyone who's listening in. So I'll be talking about a lot of the opportunities that we should be looking forward to with the Roman Space Telescope with regards to studying the dynamic galactic plane in the infrared using this superior combination of resolution, sensitivity, and field of view, and talk a bit about how current pathfinders are setting the stage for what we should look forward to with Roman in the second half of the decade. So I'll start off with some of the discussion that we've had in the earlier in this meeting, but try to put it in a more galactic context. So as we all know, we are living in this decade of time domain surveys. At the highest energies, there's Eurozeta and ArtXC who are doing the deepest X-ray sky surveys ever done. They're already, I think, into the second year of their survey, and they're creating these maps of the hard X-ray and soft X-ray sky at unprecedented resolution and depth. At the longest wavelengths, there's the VLA Sky Survey, which is creating multi-epoch maps of the gigahertz sky at very high sensitivities. And then in a couple of years, we're all looking forward to Rubin, which we've heard several times during this meeting, how Rubin will be an extremely powerful complement to Roman because of the comparable depth of about 24th magnitude. But what I wanted to focus on with this talk is, highlight some of the differences between Roman and Rubin, how and why that requires us to prepare for Roman. So, of course, as we all know, Rubin is going to be an optical survey, which means that I'm showing here the passbands of the Rubin filters, which only extend out to 1 micron, whereas Roman's power is really going to be in the infrared as this extremely sensitive near-infrared instrument with a very large field of view. And this difference in the passband makes a difference when you're thinking of galactic science. And that's because if you pull up any map of the galactic plane, here I'm showing the Gaia stellar density map, you immediately see that right when you try to look in the galactic plane where most of the stars in the galaxies live, you see there are these big chunks of dust that obscure our view in the optical. So if you can imagine what Rubin might be seeing is something that is similar to what you see on the left over here, whereas Roman will be able to see right through the dust and look at all of these stars that are otherwise hidden in the galactic plane behind these big chunks of extinction. All right, so of course, current Rubin and even Rubin's predecessors are currently limited in some sense because of these dust extinction effects. And if you fast forward 5 years into the future, when Roman will be doing its galactic bulk surveys, you suddenly run into these mind-boggling numbers when it comes to a field of view and sensitivity. So this is a plot showing the tentatively planned bulge microlensing surveys. The amount of field that you can cover is about 2 square degrees. And as well as the sensitivity, you get to about 24th AB magnitude at 5 sigma detection. And if you look similarly, if you look at the number of stars, you're looking at stars with like few 100 million stars inside this field, tiny field of view, just because you can look right through the dust in the near infrared. So not only is Roman going to be extremely sensitive and looking at so many stars, but at the same time, even the nominal microlensing surveys are going to probe phenomena on a very wide range of timescales. So if I just put the galactic plane in terms of an x-axis of timescales, at the shortest timescales, Roman, one of the core missions of Roman is to find free-floating exoplanets and exoplanets around the stars. So the shortest timescale events, which will be the exoplanets, will have timescales of minutes. And we've heard some amazing talks of the longest timescales, which are things that are extremely massive, things like free-floating black holes, and how Roman will be able to potentially give us a completely new window into understanding the remnant mass function in the Milky Way. So, even the nominal bulk surveys are well positioned to study the galactic plane in the infrared over this very wide range of timescales. And for the rest of this talk, what I wanted to motivate is that current ground-based pathfinders, it's time for current ground-based pathfinders to completely chart out the galactic plane at these timescales in the infrared to set the stage for what we should be looking for Roman and the kind of opportunities that it might offer. All right. So with that, I'll talk about ground-based surveys. So of course, as of a few years ago, ground-based surveys in the infrared did not exist. And that's because, as all of us know, ground-based infrared observing is in general difficult, which means that in the past, there has been limited experience with what to expect in terms of galactic transient science when it comes to what we might see with Raman in the near infrared. So to that end, I wanted to introduce Gatini-IR. So this is this small telescope that lives at Palomar Observatory. It's a 30-centimeter telescope with a single J-band camera. So this is 1.2 microns. And it has a single H2RG detector, 2K by 2K, with this 8.7 arcsecond pixels. And because we sacrifice the resolution with these 8.7 arcsecond pixels, we get this gigantic field of view of about 25 square degrees. And I'll come to why the 25 square degrees is interesting in a minute. But just to give you a peek, this is what a typical image looks like. This is about 1/3 of the field of view of Gatini-IR. So this is our favorite nearby galaxy, M31. It very well fits inside this field of view. The field of view is actually bigger than this because it's 25 square degrees. And the reason why this field of view in particular is important is because you can compare it to the state of the art when it comes to optical surveys today. So here I'm showing a plot showing ZTF, which is a big optical survey, pan-stars over here, and what Rubin is going to be in a couple of years. And as you can see, the Gatini-IR field of view is nearly half that of ZTF. It's bigger than that of Rubin. But I think the most important metric is that it's about 40 times bigger than the next biggest infrared camera that exists today, which is Vista, which is a 0.6 square degree field of view on a 4-meter telescope. So with this very large field of view, this really sets you up very well to do systematic surveys of the time domain sky in the infrared, especially in the galactic plane, where the galactic plane spans a very large patch of the sky, and you can look at it in the infrared with this large field of view. So again, a sneak peek into what Gatini does. It's a robotic telescope, which means that I don't have to stay awake at night. We cover about 15,000 square degrees every 2 nights to a depth of about 16th AV magnitude in J-band. And just to put that, in terms of easier language, it's about a quarter of 2 mass every night, if you just think of it. So we're trying to create maps of the infrared sky again and again, effectively close to what a quarter of a 2 mass did back in the 90s. All right. So what have we found? So we look, obviously, when we started the survey, we were looking for certain things. We were expecting certain things. And of course, there are things that surprised us during this exploration of the galactic plane in the infrared. And I, again, wanted to go back to this plot and lay out the kinds of things that we've been able to chart out in the galactic plane at these timescales. So I'll start off with some of the brightest transients that we found in this survey, which are novae. So novae are explosions on the surfaces of white dwarfs. So a white dwarf is accreting material from a companion. Every now and then, material becomes unstable and it erupts in these explosions that we can definitely see in our own galaxy and even in nearby galaxies, depending on the distance. And when we started running this survey, when we look in the galactic plane, some of the brightest transients we find are actually these extremely dust-obscured novae. So here I'm showing examples of what a typical nova looks like. So here is a new image that we got on one night. Here is a reference image from several months before. When you subtract the two, there's this bright infrared transient that sticks out. And most of these novae that we were finding were actually not even recognized in optical searches. And the reason for that becomes sort of obvious when you try to look at their light curves. So here I'm showing the J-band light curves from Gatini-IR. So this is over here, it's about 10th magnitude in J, so it's very bright. And you can compare that to, say, what an optical survey sees, which is in, say, R or G band. It's about 10 magnitudes fainter in the optical compared to the J band in the infrared. And all of that comes because of these huge dust patches that live along the galactic plane. So over the last couple of years, as we've been doing this survey, we've nearly been able to double the discovery rate of novae in our observing footprint. And most of that is because when you look in the infrared, it's really easy to identify novae because they're bright. And the brightness shines right through the dust, whereas the optical emission is completely absorbed. And so the bigger question is, what does this nova, a higher number of novae in the infrared, actually mean? So to motivate what that means, here I'm showing a cumulative distribution of the extinctions of novae that have been derived in previous optical searches up to about 2018. So as you can see, there's this distribution which goes, has a tail that goes out to maybe 10 magnitudes. So this is all optical. Now, as soon as you go into the infrared, when we started doing these infrared searches, we start seeing these extremely skewed distributions of extinctions that you can immediately see that it's much more common for us to find heavily reddened novae compared to optical searches. And you can ask the question of, does that even make sense? Because, is there really that much dust in the galaxy? And the answer to that, it turns out, is yes, because if you take recent models of the mass and dust in the Milky Way, what you see that given where most of the mass is and behind how much dust it is, you do expect to see most novae to trace an extinction distribution that's skewed towards large extinction values. And this is clearly something that was missing in the optical searches in the past, which is why the rate estimates that have come in the past have been usually, have had very large error bars or have been off by a factor of a few. And what we've been able to do for the first time, because we can look in the infrared, is to get quantitative constraints on the nova rate in the galaxy. So here I'm showing estimates of the nova rate based on different methods. So these are looking at extragalactic novae. These are looking at galactic novae. As you can see, previous optical rate estimates go, go down and up depending on what method you use. The extragalactic methods tend to be underestimate the rate a bit because of different assumptions. But now that we can do these also very large area surveys of the galactic plane, we can actually do end-to-end simulations of the detection efficiencies and the effect of dust in the near infrared, which is usually small, and try to get quantitative estimates of the galactic rate and actually arrive on a range that makes sense when it comes to the expected rate based on other estimates. All right. So, with that, I will switch to some of the most exciting timescales that I think are relatively unexplored in the galactic plane, which are the shortest timescales. So at timescales of seconds, you have things that are usually very compact, and that's why they're varying at short timescales, which are things like magnetars and microquasars, which are very compact in size. And one of the really unique modes that we have as part of our survey is this fast readout mode, which essentially allows us to expose the entire 25 square degree field of view of the detector at timescales of 0.9 seconds. So here I'm showing a movie of 0.9 seconds each. So each of these individual frames is a 0.9 second exposure of a dense galactic plane field. And right in the center of it is actually the galactic FRB source, which many of you have heard of. It's SGR 1935 plus 2154. So what we are doing in the summer of 2020 was to stare at this galactic source, try to look for infrared flares from this source, because the source is extremely dust obscured, about 10 magnitudes of extinction along the line of sight. And the persistent emission is almost undetectable. But because this was the first source where you had an FRB with a X-ray counterpart, you can look for infrared counterparts to see if you get anything over there. So as it turns out, we looked at the source for about 12 hours, about 50,000 images at the source position with 25 square degree field of view. It turns out that while we were observing, there were other X-ray flares detected during those observations, but we actually did not see anything. But regardless, because we're observing in the infrared, we can actually get constraining limits on the spectral index of the flares, just because the X-ray instrument saw it, but the our infrared instrument did not. So here I'm showing a spectrum of the FRB. So this is the famous FRB that this thing emitted. This is the fast radio burst at radio frequencies. This is the corresponding X-ray burst. And what the infrared emission allows us to do is to bridge the gap between the radio and the X-ray. Whereas, so these are the infrared limits that we have from this 30 centimeter telescope with fast readout. And you can compare that to the state of the art when it comes to optical instruments, which are nearly 2 orders of magnitude shallower, because there's this ton of dust along the line of sight. And even though there was no FRB during our observations, there were some X-ray flares that went off. These are the fluxes of the X-ray flares. And because we didn't detect anything, we can constrain the spectral index of these flares and show that if we were to actually take a random field in the galactic plane and try to look for these FRB counterparts, we actually do reach the sensitivity to detect some of these sources if the X-ray and FRB, X-ray and radio emission fall on the same power law, as was observed in the case of the famous FRB. All right. So, sticking on the theme of seconds, I'll go into some of the cool things you can see even in these accreting white dwarfs when it comes to second timescales. So, when you have an accreting white dwarf, many white dwarfs are magnetic, which means that they spin, and as they spin, the magnetic field of the white dwarf warps the accretion disk around the source. So you can expect to find that when you're looking at, say, a nova explosion in the galaxy, you might be able to detect some of these spin signatures from the white dwarf, and those will be on the timescales of tens to hundreds of seconds, depending on the white dwarf spin variables. So this is again another cool application of the fast readout mode, which was done by a talented undergraduate, Kylie Hansen, who's at MIT. And what she did was she took this fast readout mode and stared at this very bright nova that went off last year. So this is nova V1674 Hercules that went off in the summer of 2021. It was very bright in the infrared, 5th magnitude, nearly at peak. And because it was so bright, it was very easy to observe with our fast readout mode. And what she did was she stared at this source using this mode for several nights around the peak of the outburst and tried to look at short time scale variability at 1 second. So we do not find any second time scale periodic variability for sure, but we do find evidence of variability that's that has timescales of more like minutes to hours. And this is not, and we don't have a very concrete explanation of what causes this, but this likely has to do with the outflows from the nova as they're happening in real time. All right. So now that we have gone from weeks to seconds, let me go back to the longer time scales. So now that we've been operating the survey for nearly 2 years now, more than 2 years now, what we are able to probe now are things that happen on very long time scales. And these are the kinds of things that you might expect to find from accreting binaries, compact objects around other stars, or even dusty variables, Mira variables. All of these phenomena happen at timescales of months to years. And one of the really recent developments that have happened that have enabled us to look for these things is a photometry catalog. So what we've done is that we've gone back to the database of all the images that we have and essentially created light curves of every single 2-mass source in our field of view. So this plot shows the number of photometry points that you have as a function of position in the sky. And what you're seeing here is that in total, we have about 25 billion photometry points over the last 2 years. And that comes from, and most of that is near the galactic plane because that's where all the stars are. So we are planning a data release for this data set very soon. So if you have a favorite 2-mass source that you want to know what it's been doing in the infrared for the last 2 years, this is a good data set to look at. So with this large data set, what we can, this allows us to prepare for is really some of these synergies with multi-wavelength surveys that I was mentioning. So as many of you know, this is a really recent image from the eROSITA Sky Survey, which is created by far the deepest sky map in the X-ray sky ever made. And the stuff that, obviously I'm interested in are things near the galactic plane. And you see the galactic plane is quite clearly visible over here. And you see these tiny point sources that live along the galactic plane. These are all accreting neutron stars, black holes, and even white dwarfs. And the advantage of going to the infrared is really that if you take up any of these random X-ray sources, what you will typically find is that there's maybe some inconspicuous red dot over there in the pan-stars image, which is a very deep survey. But as soon as you go to infrared, even in 2-mass, you see that these are booming bright in the infrared. So light curves of these sources, which we have many of, allows us to look at the variability from the donor and understand the evolutionary state of the donor, what age it is, and relate that eventually to things like how far the binary is and how it might have been formed through the supernova that created the compact object. And then, of course, we can use the same light curves to understand whether the donor itself is causing the X-ray variability in the accretion source. And this is something that we recently demonstrated with this very bright hard X-ray transient that was discovered with SRG, where we showed that we can associate the dust formation episode in the Mira variable to brightening of a neutron star or black hole in a wide orbit X-ray binary system. All right, so I won't have time to go into all of the other variable stuff that has been happening, but I just wanted to give you a sneak peek, which is that we've been looking at all kinds of variables. We have very dusty R4 variables, very obscured young star outbursts that are, some of them are almost exclusively visible in the infrared because they're extremely obscured. This is an example where you see a nebula around the compact object. This is an example of a wide Wolf-Rayet binary that shows variability. And of course, it would be a crime for me if I didn't mention microlensing events. We do find many microlensing events. They're more of a contaminants for us, but this is a particularly interesting example of a microlensing event from what appears to be a binary lens. And we have a catalog of these that is being in preparation by Shemek Moz and team. All right, so with that introduction, I wanted to spend the last few minutes talking about what we should expect and hope to learn with Roman. So here, so just to motivate the discussion, here what I'm showing is a map of the central galactic bulge with the color scale showing the average extinction towards most of the mass along that line of sight. So most of the mass is obviously near the galactic, the center of the galactic plane. There's also very dusty, so it's difficult to view at any wavelength. And I overlaid here the planned Roman galactic exoplanet survey fields. It's a relatively small patch of the galactic plane. It's slightly off the galactic plane, although I think that's still being decided. But for this talk, because we're thinking of time domain surveys, I wanted to be a bit more adventurous and just think about the prospects of what could Roman do if we had a galactic time domain survey that scans the galactic plane. So here is my idea. So what I did was I took the Roman galactic Roman field of view, and you just imagine a simple survey that scans the central galactic plane, and and just continue scanning it along this axis. And one usual good way to quantify how much Roman could probe in the galactic plane is asking the question, how much stellar mass can you probe in the infrared if you had a survey like this, just scanning across the galactic plane, and how much observing time would that take? So here is the resulting plot. So this is a relatively simple simulation, so take it with a pinch of salt. But what I'm showing here is that if you did a survey like this, scanning from say -50 degrees to 50 degrees in galactic latitude, this is the amount of stellar mass that you're probing in the galactic plane, right in the center of the galactic plane, and and this is the amount of observing time that is required. So the main thing that I realized is quite interesting is that in just 8 hours of observing time, which is about one night of equivalent of ground-based observing time, you can get nearly more than a billion solar masses of material so in the galaxy, and that's about a quarter of the stellar mass in the galaxy. And these are quite mind-boggling numbers, because you essentially think of spending one night on a telescope and getting a snapshot of a quarter of the stars in the galaxy, just because you're looking in the infrared, where the extinction allows you to, the lower extinction allows you to probe right through the galaxy. And the one thing that I realize is that probably the bulge seasons are going to be oversubscribed in some sense, because the bulge microlensing fields will be up. But one could even imagine that if you look at especially things that are slightly away from the bulge, there is still a lot of stellar mass that you could probe in a simple survey like this that goes along the galactic plane, allows you to get a significant fraction of stars in the galaxy and is still visible outside the galactic bulge seasons because they're in the galactic disk. So you can compare this to what, say, for example, what Rubin could do. So I did the same simulation, which is take the Rubin field of view and take it across the central galactic plane. And here is the same curve for Roman. What you see is that Rubin takes a much smaller amount of time. So compared to the say 8 hours that Roman takes, Rubin can do it in say half an hour because of the much larger field of view. But at the same time, you see that it comes nowhere close to what the amount of mass that Roman can probe in the galactic plane, because even in R band, you're just, you're blind beyond a few kiloparsecs because of extinction. So, so obviously, there's this complementarity here, because Rubin is almost made for these time domain surveys, whereas Roman will probably be better at doing high resolution, slow time domain surveys. And that's something that I wanted to highlight, which is that there's this unique opportunity for you using Rubin and Roman together. Rubin will provide the long baseline regular photometry, and Roman could do slow surveys of the galactic plane that allows you to get complement these much higher time sampling ground-based images to the high resolution images that Roman will get on a slower time scale. So with that motivation, I just wanted to end with synergies with upcoming ground-based surveys. So I think when it comes to transients, a simple galactic plane survey, time domain survey, will be able to detect all kinds of accretion outbursts across the galaxy, novae, YSOs, all X-ray binaries, even on the other side of the galaxy through the galactic disk. And one particular area that I think Roman will particularly be very new at would be allowing us to look at the quiescent counterparts of these sources, because those tend to be faint. We don't know where they are before these eruptions occur. And the sensitivity and the resolution of Roman will allow us to routinely identify and categorize what are the counterparts, what evolutionary state are they at, and try to understand how these eruptions actually affect these systems in the galaxy. So this goes all the way from young stellar objects, which the Roman resolution will allow us to resolve outflows in these things. If you look at accreting binaries, the faint quiescent counterparts are usually very difficult to get in pre-eruption imaging, because they tend to be faint. But a time domain survey with Roman, you could get periodic variability from these sources. And of course, things like more rarer things like stellar mergers in the galaxy, which we know of only a handful of. But even from the previous events, we know that this is a particularly spectacular example where you see that this binary variability that was detected before the eruption allows us to show that this was there was a common envelope event that ejected this shell and caused this brightening in the optical band. So with that, I will just end with a timeline of ground-based infrared surveys and how we are getting ready for Roman, the kind of data stream that Roman may be able to provide in the galactic plane. PGIR is already up and running since 2018. Very soon, in the summer of 2022, there's going to be Winter, which is being built at MIT. Should look at Danielle Frostig's poster about Winter, which is this smaller field of view but deeper infrared survey that will be looking at the galactic plane. Rubin is coming online in 2024 in the optical, and eventually Roman will teach us so much more about the galactic plane starting 2026. So with that, I will end with this picture of all of our novae right along the dust lanes of the galaxy as viewed from Palomar, and I'll take any questions. Thank you.
Thank you very much. I don't see yet any questions in the chats. Maybe I'll go ahead again and ask the question. Do you already have a plan on setting up coordinated surveys?
I'm sorry, can you repeat that again?
Have you already set up coordinated surveys? With your current surveys on Cassini?
Oh, right. So for the last a couple of years almost, we've been, so part of the main things that Cassini does is a survey of the galactic plane. So we've been monitoring the galactic plane every single night. So that's been a central part of the operations of the instrument, which is this one-day cadence survey of the galactic plane since about 2019. Yes.
Okay. There's a question from Rachel Street. Coordinating observations of a wider region in the galactic plane would be super valuable to a lot of science. What Roman filters would you include?
Yeah, that's actually a great point. So yes, I think coordinating, especially between the capabilities of what Rubin can do and what Roman provides is going to be super valuable. And I've thought a bit about this, but I think what might be particularly interesting is having some overlap in the wavelength coverage between Rubin and Roman. So for example, if you took the J-band filter in Roman and use that as as a close approximation to what Rubin will do in Y-band. So if you were to coordinate observing, then maybe Rubin will be doing Y-band. So maybe with Roman you could do J-band and K-band. So J-band gives you that closer overlap with the Rubin data, and K-band allows you to go much fainter and look for things that are much further away. So yeah, that was just some thought that I had, which is just keep some overlap with the ground-based surveys in the let's say far red optical near infrared, and keep something that's unique to Roman, which is in the near infrared, the thermal infrared, 2 microns.
Okay, one more question by Monica Soraisam. How many transient variable stars do you detect per night with PGIR?
Okay. So that depends on I guess the definition of a transient. So yes. So we let's see. So I think in terms of the way it works is that we run image subtraction on all of our images, and all of the things that are detected as statistically significant in that are passed through a machine learning filter. And I can tell you that in terms of things that are genuinely varying, those numbers are of the order of, let's say, 20,000 per night, depending on the time of the year. Because as soon as the galactic plane rises up, the galactic bulge rises up, there's this huge increase in the number of transients, in the sense that these are also variables in the galactic plane. And at those times of the year, we can get up to maybe 50 to 70,000 transients per night. These are all real variables in the galactic plane. But at other times of the year, when the galactic bulge is behind the sun, it can go down to maybe 20,000 a night. But I think so those are the transients plus variables. If you look at just the transients, I would say that's a much smaller number. Those usually, if you look at active transients, there's probably around maybe 50 at any given time. So these include all kinds of YSOs and CVs and novae and other types of outbursts. Yes.
Okay, just a comment from Rachel Street, also on the Slack chat. Ruben are exploring a number of alternative guide plane survey strategies, including cadence filter, field and filter selection. It would be great to coordinate.
Okay, right. Yes, totally agree with that. Yes.
And then Joe Mass says, great talk. You mentioned having light curves with 25 billion photometric observations of 2 mass sources.
Yes.
Do you plan to host a database with an API that researchers and other archive systems could link to?
Yes, great question. Yes, so this is work in progress. Yes, so I think as of a couple of months ago, we created the catalog. Right now, we are trying to clean it up a bit to get rid of things, bad data, and so on. So that is taking a bit of time. But yes, the eventual plan is to do a big data release of all of these photometry data, and so we will release some note somewhere announcing this data release. So keep an eye out for that, but that's coming very soon.
Okay, thank you.
Thank you.